Okay, guys, so today we're going to talk about four trends, important trends to be able to recognize from the periodic table. All four of these trends are going to be related to how large an atom is and the charge of its nucleus, also known as the effective nuclear charge. So the charge of the nucleus itself comes from the protons. So for example, if we're talking about magnesium, this number would be 12, positive 12, right? And each of these outer electrons would feel a pull resulting from that positive 12 charge, and also from the distance from the nucleus to that electron. The effective nuclear charge, though, is simply the difference between that positive 12 charge and the number of shielding electrons or core non-valent electrons that are in the magnesium atom. So magnesium has a total of 12 electrons, but if two of them are valence, that leaves only 10 core or shielding electrons. So the effective nuclear charge of magnesium is 2 because its Z, or proton number, is 12, positive 12. And its shielding number, which are the core electrons in the first and second energy level, shown in green here, would be 10. So 12 minus 10 is 2. And that's what effective nuclear charge is. It's going to affect a lot of our trends here as we go. So let's take a look at the first trend, atomic radius. And of course, you can pause and write this down, but atomic radius is just half the distance between the nuclei of identical bonded atoms. We do that because, of course, it's very difficult to say where the edge of the atom is. So if we just take half the distance between two nuclei within an H2 molecule, it makes it much more definite. The group trend is that atomic radius will increase down a group, and because as I go down a group, let's say from lithium to sodium to potassium, I'm adding an energy level each time. Period trend is a little bit more unexpected. Even though the atom is becoming heavier and more positive, it is actually getting smaller in size, and that's because of that increased effective nuclear charge. So the effective nuclear charge for carbon is bigger than boron, so carbon is slightly smaller in radius. And its shielding number, or its number of core electrons, is the same, though, because it's in the same row. Okay, so the period trend is the size does decrease, but the group trend is much more dramatic than the period trend. All right, next up we have ionization energy. This is the energy needed to remove an electron from an atom. The group trend, and this actually is a group trend here. It's a little confusing because they're shown horizontally, but it's lithium, sodium, potassium, and those are all in group 1 of the periodic table vertically with lithium at the top. So the group trend is that ionization energy decreases as we move down a group because of that increase in radius between the positive nucleus and the valence electrons that are going to be lost. So trying to remove an electron from lithium is going to take more energy than trying to remove one from sodium. Even though sodium has a more positive nucleus, remember radius is even more important in Coulomb's law than the difference in charge. The same thing for potassium. Potassium is getting larger, so even though it has a plus 19 nucleus, that negative 1 electron is less attracted to that nucleus than sodium's or lithium's. The period trend is that as we move from left to right, the nuclear charge is going to increase. It's going to become more difficult for us to remove an electron, so the ionization energy goes up. All right, then electronegativity. So when atoms share electrons, their nuclei have a certain amount of pull on those shared electrons. We call that covalency when two atoms are sharing the same electrons. And so this happens in molecules. So the group trend is that it decreases down a group because the atom is getting larger. And because it's getting larger, those covalent electrons, those negative electrons, say, for example, in this carbon-fluorine bond, are going to be pretty close to that positive fluorine nucleus, and so they're going to be very attracted, and so therefore fluorine has a very high electronegativity. If carbon were bonded to iodine instead, the electronegativity for iodine compared to fluorine is going to be pretty small because iodine is quite a bit larger. They're in the same group, but iodine has a few extra energy levels. The period trend has to do with nuclear charge or effective nuclear charge. Again, as we go across a period, effective nuclear charge increases, thus pulling in those negative electrons more. And lastly, we have electron affinity. So electron affinity is the energy exchanged, usually exothermic, usually released, um, as, oops, my mouse is going crazy, there we go. Usually released, usually exothermic. It's the energy exchanged as an electron is gained by an atom. And so if we look at the group trend from, let's say, fluorine to chlorine to bromine to iodine, it is, with the exception of chlorine, and chlorine is a little bit different, but for the most part, as we go down a group, we see electron affinity become less exothermic. Now, electron affinity has a lot of exceptions, and we'll talk about a few of those in just a second. But the general trend is it decreases as we go down a group because the nucleus being further away from the electron that's being gained means that it has less affinity or less attraction for that electron. So less energy is going to be released as it gains an electron. Now, the period trend is the same as ionization energy. It increases as we go left to right, and this is because as atoms get smaller, they're going to pull in those electrons with more force. Another way to look at it is from a standpoint of stability. So like, for example, fluorine gains a lot of stability by gaining an electron, and so it becomes like neon. And so by becoming like neon, it's going to give off a lot of energy because it's now in a lower energy, more stable state. There are a couple of weird exceptions, like nitrogen is endothermic instead of exothermic, and it sits right here in the nonmetal. So why wouldn't gaining one electron be exothermic and represent an increase in stability? We typically think of nonmetals gaining electrons, and nitrogen can. The problem is with electron affinity, and specifically we're talking about first electron affinity. If we look at the orbital filling notation for nitrogen, it starts in its ground state before gaining any electrons with these three up arrows. So one electron in each of these three 2p orbitals. That represents a certain amount of symmetry and therefore stability, as it turns out, for the nitrogen atom, even though the nitrogen atom is not totally stable. The problem is by giving it an electron right here in one of these 2p orbitals, you lose some of that orbital symmetry, meaning we don't have three up arrows. So it becomes less stable. And so it actually takes an input of energy to add an electron to nitrogen. Okay. Now, once you add a second and third electron to nitrogen, there you're going to see an exothermic. As it becomes like neon, it's going to become an exothermic process, because becoming like neon by gaining three electrons, which if you'll recall, nitrogen as it forms nitride does in fact gain three electrons. That represents a great increase in stability, unlike just gaining one. So there are some weird things that happen with electron affinity, and I just wanted you to be aware of, generally speaking, how at least one of those can happen. You can kind of see the same thing here with lithium. You wouldn't expect a metal to ever gain an electron, but by gaining one, it fills up its 2s orbital, which represents a slight increase in stability, and therefore it's an exothermic 60 kilojoules per mole. Beryllium, on the other hand, already has a filled 2s orbital, and so by gaining an electron, that would jump it all the way over to the 2p, and that's not a very stable place to be. So having those orbitals filled, or at least symmetrical, like in the case of nitrogen, does represent a slight increase in stability. All right, the last thing I want to show you is just sort of the general trend pattern here. You'll notice that ionization energy, electronegativity, and electron affinity all follow the same trend. They go up as we go up and to the right. Another way to say that is nonmetals tend to have high ionization energies, tend to be very electronegative, and tend to have great electron affinities, or at least greatly, exothermic negative electron affinities. And then things that are metallic tend to have larger radii, larger size atoms, but have the opposite: low electron affinity, low ionization energy, and low electronegativity.